Good afternoon, everybody. My name is Mark Melhus. I'm the assistant professor in physics department. I got my PhD from Northwestern 3 or 4 years ago. 3 years ago. And before that, I also got a master's from Northwestern. I have a master's in mechanical and aerospace engineering from IIT, undergraduate degree in physics from the University of Chicago. I've taught at a number of other institutions as an adjunct and part-time professor, and this is my first full-time position. Very excited to be here, and I like the school a lot. That enough? All right. Okay. So, the focus of my research is granular materials, particularly the nonlinear aspects of them. And for today's talk, what I wanted to discuss was some of the interesting aspects and details of granular materials. In particular, the challenges that they pose towards doing research with them, and the paradoxical and unusual effects that they produce. I've got a few demonstrations here as well that I'll trot out at the appropriate times and pass around. I just ask that you don't open up the jars of sand, because if you do, I'll explain them as we go. Anyway, I'm working with Will Dinwiddie, who's over there in the Eureka program, and the other thing I want to say is I prefer a very interactive style of talk, so if you have any questions, go ahead and either just ask, or if I'm in the middle of a long exposition, you can pop your hand up, or just wait till I finish. But feel free to chime in at any time. I don't want to just stand up here and tell you things. I want to interact with you. So, today, first I want to talk about why granular materials are important, and then some of the fundamentals of how they behave on a microscopic level. For microscopic in granular materials, it's not as microscopic as, say, particle physics or chemistry level stuff. But they're larger, but there's still small scale stuff that happens, and then there's large scale stuff that happens. Talk about the large scale stuff next, and then finally I'll talk about the current research that we're doing and how these methodologies impact it. Here's one example of a granular flow. It's a typical hourglass, and you can see the sand comes down through a little hole in its pile. You've all seen an hourglass, I assume, right? Someday I should buy one. I'm going to bring one of these things. It's difficult to justify research behavior for some money to spend on something that everybody's seen already. So maybe they'll build one. We'll see. Okay, why study granular materials? Granular materials are all around us. They're ubiquitous. The earth we walk on is a granular material. Gravel, sand on the beach, go to the dining hall, salt, sugar, pepper are all granular materials and shakers that we use. Now, admittedly, the behavior of salt in a salt shaker is not that complicated. And, you put enough on your food, you're good. But it's a good model for a lot of other things. And in many industries use granular materials. Obviously, construction, they're digging in the dirt and building things like that. Mining, agriculture, pharmaceutical industry, there's a lot of work with powdered materials and mixing problems there. Food manufacturing, food production, seeds are, corn in silos are granular material. It's a great model system for what happens, how grains interact. So there's a lot of places where granular materials come up in everyday life, and they have unusual enough properties that they're worth studying. And I'll talk about those properties now. First of all, we'll define them. What is a granular material? It's a collection of small microscopic grains. In essence, it's a simple system, but it has a lot of complex behaviors: segregation, fluidization, surface waves, force change, bistability, a number of things that all these terms I'll explain as we go on. These are all complicated and different things that happen. Some caveats here. We generally don't want to work with things that are small enough that static electricity effects are dominant. Those are more in the range of powders. So a typical granular material will be on the order of 50, 100 microns, millimeter, 2 millimeters, 3 millimeters, all the way up to, I guess you could call a collection of, 1,000 bowling balls a granular material, but it's, doesn't exhibit a lot of the classical behavior of smaller particles. You put enough energy in it, it will. So take a really big box and put in 1,000 bowling balls and shake it hard enough and they'll go flying around. So I don't want to be anywhere near it when it happens. So that's sort of the size ranges and materials we're talking about. Usually the grains themselves are solid. They can be spherical, they can be cubic, they can be irregular, oblong. You know, rice is a really good granular material. A lot of people have done experiments with rice. Actually, an experiment that made the cover of Nature, someone used M&Ms to work out the fact that they pack more densely than spheres do, because they're in the oblong shape, they can move around. So, you know, the cover of Nature, is really prestigious scientific magazine, had a big sphere full of M&Ms, and that was the guy's research. Sounds like fun research, but I'd want to eat the experiment afterwards. Anyway, so that's what a granular material is. M&Ms are one good example. So they're a little big. I typically work with sand. Sometimes we use small brass spheres, so the smaller size means we can have a lot more stuff in a bar. If this were full of M&Ms, I'd have like 40 of them here. And now I've got, you know, maybe 10,000, 30,000 grains in here. I haven't estimated, but it's a pretty large number. So I get better statistics. Okay, surface interactions. Behavior of the granular materials is dominated by surface interactions. It's particularly interesting because two grains that are in contact, they exhibit a force on each other, a contact force when they push, and a torque. If this grain is here, it'll be torquing this grain in that direction, and this grain will be torquing in that direction. The grain can also have other torques on it that it applies. You know, if this grain is being twisted by other grains, it'll apply that torque to this grain. So they kind of behave like bad gears in that way. In that those contact forces, they can either roll against each other or they can slide, and then there's frictional forces. Those surface forces dominate the behavior on the small scale of granular materials. But the other thing that's important about is that if that gap, I have no idea what that is. I don't want an important message right now. Thank you. And right where I was about to point, of course. So if the gap between the two materials becomes non-zero, then the forces and torques go to zero almost instantly. There's one small caveat to that. Very fine grains in air can have interactions that the air between the two particles can cause certain behaviors. That only comes up in very particular cases. So most granular experiments can be done in air, but there's a few that have to be done in vacuum to limit that, eliminate air forces. And if there's a liquid involved, like wet sand, the water forms a little bridge in here. And because of surface effects, the surface energy of the water, the bridge actually pulls the grains together. So it makes them clump together more tightly, and it provides a resistive force about pulling them apart. If you ever tried to build a sandcastle with really dry sand, you know it's kind of impossible. But with wet sand, you can do all kinds of things, make vertical shear walls. I actually saw a picture online as I was putting this together of a sandcastle arch, a literal arch made of sand. You know, so at the top here, it's completely unsupported. It's all held up by lateral forces from the sides. And if that were dry sand, of course, there's no way you can do that. So the hydration, the amount of moisture in the material, is another variable that we can play with. And you know, you get good experimental controls, another dial you can turn to see, look for different behaviors. So that's the small scale stuff. The nonlinearity of these interactions, the fact that the change from complete or almost complete force transmission with a contact to virtually no force transmission with a tiny space really means that there's a lot of variability. It's a nonlinear interaction. You know, typically in science, we like to look at linear behaviors. You know, I double the strength of the force, the acceleration doubles. I double the mass, the amount of force required to move it is cut in half. Linear relationships. The force relationship in granular materials in terms of contact distance r, we'll call this 0. Let's draw the axis correctly for that then. This is r, the distance between the particles, and that's 0. Contact forces are basically 0 when r is positive, and as r gets negative, they get very large. When we're trying to take two grains and push them into each other, large forces come up. So this is very steep here. It's almost digital. A lot of the simulations, including the one that I did as part of my PhD thesis, basically assume that particles are in contact, the forces are large and significant. There's a Hertzian contact model, has some deformation of spheres, and it's got some complicated math involved, so I don't want to go into a lot of details. But the gist of the model is that once they're not in contact, the forces are zero. They have very steep behavior, it's almost digital, on and off. And in the soft contact models, they use the amount of overlap to determine the contact forces. So you get behaviors like, if you have a slope here, grains on the top flowing down the slope, there's some sort of characteristic depth of this flow, and underneath that, there's virtually no flow at all. This is a time-lapse photo over about 6 or 7 seconds. You see several particles go shooting by, and the ones that are fixed, they were emphasized with the pink dots. The pink was added later to the picture. And those are the ones that are basically static, not moving so little that they can identify a clear center. Question?
Yeah, what curve is that? Is it
Oh, that's I'm sorry, I didn't label the y-axis at all, my fault. The y-axis is basically the interaction force between the two particles. And in this direction is distance, and that's force. Let me fix that error. Thank you for pointing that out. One of the things they tell us in Teacher 101 is when we put a graph up, always label the axes.
Really?
Force, distance. Always have to remind myself, because I know what's on the axis. But I have to make it clear to you guys, and that's the important thing. Okay, so back to this model here. All these grains are static, and these are flowing. If this were a fluid, we would expect some differential equation to govern the behavior, and you see the velocity decreasing as you went down the pile and have a very long depth. But literally, if you had a box this big full of fluid that was flowing like that, you would see flow all the way at the bottom. It would be very slow, and at the boundary, the very boundary, the bottom of the whatever your container is, that's where the flow rate would go to zero. That flow is called a Couette flow. It's basically linear shear-driven flow, and it's completely linear in terms of the velocity response. Here we get a Couette flow in a narrow band. The velocity in this band tends to go linearly. At the surface, it's got some characteristic value, decreases to zero, and then beyond that, it's zero. And that's the unique thing about granular materials, that particular flow. Down here, I've shown one particular behavior in oscillon I'm going to talk about a little later in the talk. This is in a vertically vibrated material. We take basically a dish of the material, circular cell, put in a layer, not too thick. I think this was done in about 8 particle diameters deep layer. And pump all the air out, because the air makes a difference for these interactions. And then you start shaking it up and down. And a whole regime of things happen, which I'll talk about later in the talk, as you change the frequency of the vibration and the acceleration. It was a rich phase structure that I didn't want to go into in great detail, but I'll show you some of the patterns that form. And another thing that's important is the exact configuration of the grains can make a lot of difference in the behavior. In this particular example, you can see that some of these grains are clearly in contact or close together. These two look pretty close. Here there's a large gap. You can see gaps there, etc. That's the particular configuration of this granular bed. And the exact details of those configurations control or dictate some of the behavior of the granular materials. Usually they fall into a regime that we can classify, but I'm going to talk about the configurations next, I think. Yes, force chains. So in a bed, if two particles are in contact, they can transmit forces. If they're not, they can't. In this picture here, the red particle all the particles have some mass, but the red particle is the one we're interested in, and it's touching these two, we're touching these two, and you can sort of map out the force contacts that govern how this particle is eventually supported by the bottom of the container, because the bottom and the sides are where all the mass is supported. So force here, force there, forces over here. But you can notice this particle down here doesn't seem to be carrying any of this particle's weight at all, and up here this one is, and it's sort of higher than that one. So it's not exactly a smooth, simple curve. If this were a fluid, we would expect a simple relationship between depth and pressure, and because it's uniform hydrostatic pressure, we would expect that this particle is supporting a certain percentage of the weight of everything above it. It doesn't matter if it's here or there. In granular material,